And we are going to get started. Hopefully the last couple of people get here shortly. And if not, they can watch the recording. All right, so we're going to get started by finishing up the last half of the section 3.2 presentation, dealing with the last couple things we want to talk about in chapter 3. And then we'll look at some examples of the scatterplots, correlation, and our least squares or regression, and talk about those. So let's do the sharing of the screen. That one, maybe go again. Aha. All right, excellent. All right, so this is where we left off, though I did not show you guys this screen. This was the next screen in the presentation from where we stopped yesterday. So one of the other important things that we want to, and I want to show you and talk about is these computer regression outputs. There's a couple of different formats that these can be provided to you in, and they do very commonly show up on the AP exam. So it's really important that we know what they are and how to read them. So a number of statistical software packages produce similar regression output. We need to be able to locate the slope, B, the y-intercept, A, in our y equals A plus BX formula, and the values of S and R. Remember, this is the standard deviation of the residuals, and R squared essentially how accurately the regression line accounts for all the variances of the residuals and how accurately it will predict a given value of y based on x. Kind of what R squared represents. All right, so we have these 4 things we need to be able to find. The first output we're going to look at is from a program called Minitab. We haven't really used it in this class because it's not a program that I have access to, but it is a statistical program that can do many things. One of them is give us this regression output. So at the top here, we kind of have headings, right? Predictor, coefficient, standard error coefficient, T, and P. We get T because if we're doing a test involving these things, it's a T-test, and obviously P for p-value. We're not using these things right now. Same with the standard error coefficient. But we do need the predictor and the coefficient. Our constant is our y-intercept. Just like in the formula for a regular linear equation, y equals mx plus b, or in this case, y equals a plus bx. The value or the variable that doesn't have an x with it is the y-intercept, but it's also known as the constant term. All right, so they're referring to the y-intercept or the value of a as a constant. All right, and this output is based on our example that we saw yesterday with the used F-150 truck and its price based on miles driven. So this is essentially saying the y-intercept, 38,257, is the price of the truck with 0 miles. Then we have miles driven, which represents our explanatory variable, miles driven, and the slope that goes with it. Now, for some reason, this input is slightly incorrect in that it does not say negative 0.16292. Not sure why it has that error, but there is an error. That should be a negative. We then have our standard deviation of the residuals with S, and R squared is R squared. In this output, R squared is being provided as a percentage rather than a decimal, but we could easily convert that to a decimal if we need to as 0.664. We don't need to worry about this adjusted R squared. All right. So this is how we can find those values we want in this output. We'll see an example of this later. So that's one way we can see this. This is a separate output from a different program. I'm not entirely sure which program produced this output. But again, we have these headings here. In this one, they're bold headings. So we have summary of fit and we have parameter estimates. Again, R square is R squared. So that's kind of nice. Typically, it's kind of written out as what it is. All right. And then the root mean square error is our standard deviation of the residuals. And that you're just going to have to kind of remember that that's what that one is. And we can maybe tie a connection to the root being a square root, in that the standard deviation is typically the square root of the variance. So if we want to take that as a cue that this is the standard deviation of the residuals, or S, that might be helpful. And then we have our parameter estimates, and we have the heading term, estimate, standard error, t-ratio, probability. And again, the intercept is the y-intercept, so that's kind of nice. It's written out for of A. And then again, our miles driven is our explanatory variable, and it goes along with the slope or value of B in the formula. This time the output is correct. It is a negative 0.1629, as there is a negative association between miles driven and price. Is there anything I can clarify with the outputs here? All right, so then we have a regression to the mean. Using technology is often the most convenient way to find the equation of least squares regression line. It is also possible to calculate the equation of the least squares regression line using only the means and standard deviations of the two variables and their correlation R. So if we have those values already, but maybe we don't have the whole set of data, so maybe we can't put it into our calculator that way, we can use these formulas to get our regression line formula, or yeah. So we have data on explanatory variable X and response variable Y for n individuals. From the data, we can calculate means and standard deviations of the two variables and their correlation R. The least squares regression line is the line Y hat equals A plus BX with slope, B equaling R, the correlation, times standard deviation of Y divided by the standard deviation of X. We can kind of think of this the same way as how we would calculate a normal slope with a line, in that we have rise, change in Y, divided by run, change in X, if we were doing a normal line. In this case, the change in Y and change in S being replaced with standard deviation in both, but it's still Y over X. And then we're multiplying it by R, which is the strength of the association, essentially. And then notice we do need B to find our intercept. All right, the y-intercept. So A will be Y bar minus B X bar. All right, so the mean of Y minus B times the mean of X. And that will find us the y-intercept, or value of A. Once we have A and B, we then have Y hat equals A plus BX. We have our formula. Again, if you have all the data points, the easiest thing to get your regression formula is to put these into your calculator in the lists, have the calculator do all the legwork for you. And then you can use all these things in other places. Right? Essentially, we want to avoid doing these calculations by hand if possible. You will need a moment to write anything down from this screen. Also, I do believe these formulas are also on your formula sheet for the AP exam. Yep. And they should be basically the same as what we see here. So we do have both of these formulas on the formula sheet. Correlation and regression wisdom. Correlation and regression are powerful tools for describing the relationship between two variables. When you see these tools, be aware of their limitations. The distinction between explanatory and response variable is important in regression. This is how the scatterplot should be graphed here. We have miles, our explanatory variable, and then price as the response variable, and we get the desired output, so to say. We have our linear regression, the S and R squared. If we were to flip these things, we get a noticeably different graph. Okay, it'll still make a scatter plot. We'll still be able to find a regression line, but now miles driven depends on price, which doesn't really make sense. We're not going to get very good usable answers because price does not explain how many miles have been driven on the truck. All right. However, I do want you to notice R squared and also in turn R are the same for both of these. All right, so that's going to work out regardless of how you order this data. But again, that's from what we saw in section 3.1, that the correlation R, which also means R squared, doesn't care which one's explanatory and which one's response. When it comes to finding S and finding your linear regression line, at least squares regression line, we need this to be in the proper order. Number 2, correlation and regression lines describe only linear relationships. So below we have 4 scatter plots. In between these 4 scatter plots, which one do you believe has the highest correlation? In other words, which one has the largest R value? So I want you guys take a moment, think about that, and then in the chat, please respond. Which of these 4 graphs do you believe has the highest correlation? All right, we'll do it this way. Rather than type in the chat, if you believe A has the highest correlation, please raise your hand. Devin thinks C. Okay, we'll get there too, Devin. Thank you. Anyone think A is the best one or the highest? What about B? Does anyone believe B will have the highest correlation? Okay. What about C? Please raise your hand. And what about D? Alrighty. So you are all correct and incorrect. All of these have the exact same R correlation value. They all have an R equal to 0.816. Also, interestingly enough, they have the exact same least squares regression equation as well. Y hat equals 3 plus 0.5x. Now, obviously, these are completely different scatter plots with completely different patterns. All right, if we look at B, it's obvious that this is not linear. This has a very distinct pattern. It looks more, quadratic, so to say. All right, it looks more like a curve. And so a line is not a good model for this scatterplot, even though we can make all the necessary calculations. We can put this data in the calculator, we'll get a correlation value, we can get a regression line, we can do all those things. However, that's not the appropriate model for the scatterplot. Right? Same thing for D. It's obvious that most of our points are lying right here. We have this one outlier. And so a line going this way is not a good predictor. It doesn't model the typical relationship between the two variables. Right. Even this right here, we have this massive outlier, which is going to pull this line out this way towards the outlier, which then is probably not going to make a good predictor. Although a line is much more appropriate for this than for B. Right, so we should only be using linear regression and correlation with things that can be modeled with lines. Do not make the mistake of using these things with scatterplots and data that are not well modeled with a line. You'll get quote unquote usable things, you'll get values, but they're not appropriate. So be careful. Number 3, correlation and least squares regression lines are not resistant, right? Meaning they are not resistant to outliers. So we have this example, we have age at first word versus Gessel score. Not entirely sure what a Gessel score is, but there's that. We have a main cluster of data here. We have child 19 as an outlier and child 18 as an outlier. Right, 19 is an outlier because it's kind of way high considering the rest of the cluster here. It's a little too high on the y-axis. And then child 18 is kind of far away on y and on x. And it's way away from the main cluster. So it's also considered an outlier. If we modify this data and we take all the children into account, we have the original green line of best fit or regression line. If we remove child 19, we take this one away, our regression line moves closer to the child 18 point here. We have a change in R and in the linear equation. We remove child 18 and this line makes a much bigger swing right up here. R changes, right? The slope makes a drastic change. Right? And we see some obvious adjustments to the regression model. Right? And that again is because the least squares regression line is not resistant to outliers. Right. Least squares lines make the sum of the squares of the vertical distances to the points as small as possible. A point that is extreme in the x direction with no other points near it pulls the line towards itself. We call such points influential. Right? They make that line swing. It makes a larger change. Right? An outlier is an observation that lies outside the overall pattern of the other observations. Points that are outliers in the y direction but not the x direction of a scatterplot have large residuals. Other outliers may not have large residuals. Right? An observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. Points that are outliers in the x direction of a scatterplot are often influential for the least squares regression line. Right? And that's what we saw in this example. Child 18 is far away in the x direction, also in the y direction, but not too far away from the original regression line in the y direction. So it doesn't, when it's there, right, it's very influential when we remove it, right? We see this big swing. Right? If we keep it and remove the other outlier, we don't get a huge swing because this one still pulls the line down that way. So it's more influential. I hope I did not confuse you there. Does anyone need a moment to write anything down from this screen? And that is the end of the 3.2 presentation. All right, so we looked at interpreting the slope and y-intercept of a least squares regression line. Essentially interpret the exact same way we would expect a linear equation to be interpreted. We use the least squares regression line to predict y for a given x, calculate and interpret residuals and their standard deviation using our calculator. Explain the concept of least squares. Determine the equation of least squares regression line using a variety of methods, primarily our calculator, but we can also do it if we have the means and standard deviation and correlation for our data set. We can construct and interpret residual plots to assess whether a linear model is appropriate, assess how well the least squares regression line models the relationship between two variables, and describe how the slope, y-intercept, standard deviation of the residuals and r-squared are influenced by outliers. So we have all that. Right. So now I'm going to end this. I'm going to stop sharing this screen. I'm trying to get this working the way I want it to today. See if that'll work. Do that. Do that. See if things want to cooperate with me today. One moment. That one. Sorry, give me one moment here. It works. And let's see if things want to cooperate today. That'll work. Excellent. All right, so now hopefully you should be able to see actually my document camera. We're going to look at some things here. All right, so here we have a scatter plot. So the manager of a grocery store selected a random sample of 11 customers to investigate the relationship between the number of customers in a checkout line and the time to finish checkout. As soon as the selected customer entered the end of the checkout line, there we go. Right. Data were collected on the number of customers in the line who were in front of the selected customer and the time in seconds until the selected customer was finished with the checkout. Data are shown in the following scatter plot along with the corresponding least squares regression line and computer output. All right. So here, obviously, we have our scatter plot with our regression line. We have customers in line, and these would be customers in line in front of the selected customer, and then time in seconds that it takes for them to check out. Now we have our output. Again, we have headings here: predictor coefficient, standard error coefficient, T, P. Right? We're not really worried about the ones over here. We do want to know what the y-intercept is, right? And that's our constant, which is A in our regression equation. We also have our explanatory variable, customers in line, which goes along with the slope and value of B. So we could, at this point, write the equation. Right? We can say we have y hat equals $72.95 plus 74.4. We'll leave the 0 off. X. Right, and so that would be the regression equation based on our printout. We also have S, right? Standard deviation of the residuals, and our R squared. Essentially the accuracy and how well our regression line accounts for the variance and how well it can predict a given Y based on X, or the amount of time it takes to check out based on the customers in line ahead of you or ahead of a selected customer. So the first question here, identify and interpret in context the estimate of the intercept for the least squares regression line. Well, we've already found that. That is 72.95. All right. And that will be seconds. And essentially, right, if there is no customers ahead of the selected customer in line, it will take approximately 72.95 seconds for them to complete their checkout process. All right. So this is important here. We have interpret in context. Simply providing the value is not sufficient. All right. So we can say the estimate of the intercept is 72.95 seconds. And represents the time the selected customer would expect to take to complete checkout if no customers were in front. And move that up so we can actually see. All right, now obviously the way that I've written this all around the page here is just because of spacing. Right? I printed out this question and it didn't provide space to answer. So there's that. So again, we're providing the answer to what is the estimate and then what it represents in context. All right, question B here, identify and interpret the in context the coefficient of determination R squared. I'm not going to write this one in here, but again, we know that R squared is 73.33%. Right? And essentially, that means that the linear regression, the least squares regression line, will account for the variance and provide a good estimate for the time in seconds based on the customers in line, roughly 73.33% of the time. It's like 73.33% accurate in a way. All right. One of the data points was determined to be an outlier. Circle the point on the scatter plot and explain why the point is considered an outlier. There's only one point that kind of falls outside of the general pattern. That's this guy here. All right. This point is considered an outlier because it is really outside what we would expect if there were 3 customers ahead of the selected customer in line. The amount of time that it's saying it took this one customer to check out is like less than the amount of time it would take if there was only one person in line ahead of them. Right? It doesn't fit in with the rest of the data points. Right? It's far away from our regression line in the Y and in the X direction, and doesn't fit the expectation based on our regression model. Are there any questions? Anything I can clarify? And this was a question from the 2018 AP Stats FRQs that has been released. So that's why I selected it. Now, this next series of questions is actually from the released questions from the first administration of this year's AP exam. This gives us a fairly good idea of the type of thing that's going to be on this exam for the third administration, which is the one that we'll be taking, or that you guys will be taking. So this one does not start out with a scatter plot, but it does use them after this question. Right, so attendance at games where a certain baseball team is being investigated by the team owner. The following box plots summarize the attendance measured as average number of attendees per game for 47 years of the team's existence. The box plots include the 30 years of games played in the old stadium and the 17 years played in the new stadium. Right, we want to compare the distributions of average attendance between the old and new stadiums. So when we're comparing distributions of quantitative data, which is what we have here, since we have box plots, we know it's quantitative, right? We want to look at shape, center, and spread. Those are the three main things we should always consider, right, when we're describing and comparing two distributions. The other thing we should also consider is outliers. Sorry, I forgot that one. That's an S. All right, so we want to address these things when we compare. So first, let's look at shape. If we look at the box plot for the old stadium, we could make a guess that it might be about a symmetric distribution. We won't be certain on the actual shape. We cannot say it's normal. We don't have the data to say that it's normal. But we can say that it's most likely symmetric. Right? Whether it looks like this or whether it looks like a rectangle, we don't know because we don't have all the data. Okay, but it looks like it's probably symmetric. Based on the new stadium box plot, we're probably looking at something that has a little bit of a skew. And we can tell that from the box plots. We don't need all the data to get a guess of what the shape might be. Now, because of the way they have this set up, notice these small values are at the bottom here going up to the larger values, right? If I were to turn this sideways, this is how we've typically seen our box plots in this class, right? Now, we need to think of this as reversed. Because typically on the horizontal axis, we go from small to large, going left to right. This one's not going in that direction. So that means that this box plot actually represents a skew to the left. And that's because this is the smaller value over here, the larger value over here. So you want to be careful with that. Take into account how they've done their scaling, right? And it's done appropriately if you're scaling on the y-axis, but we need to be able to know that for describing, right? We have our center here, and as far as center, like obviously they have different values for their centers, right? But more specifically, we can talk about the IQR. Right, that's a measure of center-ish. Right? And the spread we can talk about, and outliers. Right, so essentially, as far as this is concerned, we're comparing them. Right? The old stadium is approximately symmetric, has an approximately symmetric distribution compared to the new stadium, which will be skewed to the left. Right? The center portion of the data for the old stadium is a little bit smaller, right, than the center, the IQR for the new stadium, which is a little bit more large. Okay, and obviously we want to compare centers directly, right? The center for the old stadium is about 16,000 people, and the center here is going to be about 25,000, which is a huge difference, right? As far as the spread is concerned, it's easy to see that the range or the spread for the old stadium is smaller compared to the spread for the new stadium. Right, there's a larger spread here, it's a bigger line. And based on these box plots, neither stadium has any outliers. We've addressed everything, that's all we need to say. I'm not writing this down because it would take longer. Is there any questions? Anything I can clarify? Okay. Now we got a scatter plot here. The following scatter plot shows average attendance versus year. Notice that there is a differentiation between old stadium and new stadium. Right, and it kind of makes sense. They're going by year. The old stadium only goes until it's not being used anymore. Looks like about the year 2000, and then we get new stadium. We want to compare the trends in average attendance over time between the old and new stadium. All right, now we're talking about comparing the trend, and we're using a scatter plot. Right, so we want to talk about essentially the strength, direction, and form, like linear, curved, something like that, right? So if we look at these two, we can roughly sketch a regression line, right? For the old stadium, it's probably going to be something like this, give or take, maybe a little higher of a curve, I don't know, right? And the new stadium, we're looking at a curve more like this, or a line more like this. Okay, so now when we're comparing, we can say the old and new stadium both have a positive association between year and average attendance, right? The strength, right, of the association for the old stadium is weaker compared to the strength of the association for the new stadium, right? As the points for the old stadium are more spread out, essentially. They're farther, they have larger residuals compared to the residuals for the new stadium, right? But both are linear. We can model both pretty well with a linear association, a linear model. Okay, so both have positive linear associations where the new stadium has a stronger positive association than the old stadium. However you want to word it is up to you. The important thing is to note that they both have a positive association. Old stadium is a weaker association because the points are more spread out around the line than the new stadium, right? And having that positive is the direction, so to say. It's telling us if it's increasing or decreasing over time. Anything I can clarify here? So again, the things for this is to have strength, direction, and form. The next part, we have two scatter plots. Now we want to consider both of these. So graph 1 shows the average attendance versus number of games won for each year. Describe the relationship between the variables. Right. Again, we're using those same three key kind of things: strength, direction, and form. If we were to do a rough idea of the regression line here, something akin to that. I probably kind of messed that up a bit, but you get the idea. So we have something that is obviously well modeled by a line. Right? We have a positive association that is pretty strong, right? The points are nicely clustered around the line. The residuals aren't that big, right? So again, when we describe the relationship, we have a strong positive linear association between the number of games won and the average attendance. That's it. That covered all the bases. Strong, linear, positive. We've covered it all. Right. The next question here says, graph 2 shows the same information as graph 1, but also indicates the old and new stadiums. Does graph 2 suggest that the rate at which attendance changes as the number of games won increases is different in the new stadium compared to the old stadium? And based on what this looks like, I mean, even if we just use the pen here, it's pretty much linear the whole way. Like there's not a real change in direction when we only look at new and only look at old stadium. Right? That means the answer to this question, no. It doesn't suggest that the rate at which attendance changes as number of games won increases is different for the new stadium compared to the old stadium. Right? We have a strong linear relationship throughout, just based on graph 1, right? But there is no real significant change in the direction of the line. Okay, so there's no real evidence for it being different. Right? The rate at which the attendance increases as the number of games won increases stays fairly consistent between the two stadiums. Any questions? All right, the last question here says, consider the three variables: number of games won, year, and stadium, based on the graphs, previous page. Explain how one of those variables could be a confounding variable in the relationship between average attendance and the other variables. Okay, so games won, year, and stadium are three variables that we're using and comparing against the response variable of attendance. Right? Now, as far as a confounding variable, something that doesn't necessarily depend on which stadium is games won. Right? That's a consistent thing throughout, whether we're in the old stadium, new stadium, or whatever year it is. Right? The problem is that between the two stadiums, right, whenever they won more games, attendance increased. So we don't know if the increase of attendance was due to there being a new stadium or because they were winning more. So that makes it a confounding variable. We also don't know if they were winning more because they had developed their players more over time, right? So the year doesn't really help, right? Maybe they got better and they started winning more games, over time, and so people attended more. Or maybe people are coming because they got a new stadium and the players decided that want to play better in a new stadium. Who knows, right? So the number of games won is the confounding thing. It makes it so we can't differentiate between which variable is the cause of the increased attendance. We don't know if it's the year, we don't know if it's the stadium, we don't necessarily know if it's just because of games won. Right, so we kind of come to the conclusion that games won is our confounding variable. It makes it so we cannot tell which of the other variables are causing a change. And really in a question like this, you want to be able to reason as to why you're selecting that to be the confounding variable. There has to be a reasoning based on the data. So you might be able to make an argument for one of the other two variables. This depends on your understanding and how well you can explain it. Is there any questions? Alrighty, stop that. Cool. So, with that, next week, which all intents and purposes, that will be basically the last couple times I see you guys before the AP exam. I believe we will still meet the day of the exam. We have a scheduled class that day. However, I don't know if any of you have any other exams going on that day in the morning session, right? Our AP exam is the afternoon session of testing window. So next week, we will be going over sample free response questions from previous year exams and also looking at the grading rubrics that go along with those questions. So we can get a better sense of what graders are looking for when you write your responses. And also help us do like review of a lot of the concepts that we've seen so far this year. So that's the plan for next week. Also, which I believe I said yesterday, we will, hopefully by the end of today, I should have the last multiple choice assessment ready for you guys, which will cover chapter 11 and chapter 3. It's probably going to be about 15 questions, but that will be the final assignment for the course. There will be no other things essentially assigned that you must turn in for a grade. That's going to be the last thing. There will not be a free response question assessment for this last unit of a couple of chapters. So you don't have to worry about that. The AP exam will be enough. Are there any questions, comments, or concerns before I let you guys go? All right. And so then the other thing is, again, if you have not logged into the testing app, which is different than logging into AP Classroom. Right? If you've not opened and run and logged in and done one of the like practice exams and gone through the practice of like setting up your exam, you need to do that. Right? Don't wait till the last minute. We need to make sure that you're able to log in, things are working. If you don't know your username and password for College Board and AP Daily and all that, or an AP Classroom and all that, you have to call like the helpline from like College Board to get that stuff recovered, right? And that unfortunately takes about 20 to 30 minutes to go through that process. Right? You will not have time to do that the day of the exam. Okay, so don't wait. If you are choosing not to take the exam, don't just choose not to show up. And it doesn't look good. Yeah, it's not what you want to do. If you do not want to take the exam, you've already decided you're not going to take the exam, you need to cancel it. You have up until 8 days before your exam to cancel, which means we're running out of time. Okay. To cancel, you need to send a message, send an email to your testing coordinator at your school site, For Orange Glen, that's Miss Amy Booth. At San Pasquale, that is, oh man, what's your name? Forgetting people's names now. Miss Jennifer Franey. Right, Miss Franey, she's your testing coordinator at San Pasquale. And for Escondido, your testing coordinator is Miss Kelly Ladendorf Bowden. All right. If you're choosing to cancel, you must email those people. I cannot cancel your exam. I appreciate being in the loop, but I can have nothing. I can't do anything on the exam side. Your coordinators must do that. Right. If you are taking the exam, then you need to make sure you've logged into the app and that it works. Please. Sorry, this is gonna be something we talk about every day until the exam. All right. Other than that, I hope you all have a great rest of your day, and then you have a great weekend and a great beginning part of your week next week, and I will see you next week.